So in this video we're going to continue looking at different kinds of metrics, and we'll start by looking at the discrete metric. And this is a pretty abstract idea but very important one. So let's just draw this out. Number 2, the discrete metric. And this metric can be applied to any set. So we define it by distance function d from 2 points in any set x into the reals, and this takes our points to a piecewise function which is defined as 0 if x is equal to y and 1 if x is not equal to y. So what is actually happening with this function? What is this notion of distance that we've drawn? Well, if we take just any set, say x is just a set of points. Remember, these don't have to just be sets of points. This can be absolutely any set. This could be the real plane. This can be three-dimensional space. This could be a cylinder. It doesn't matter. Just any set of points. And what we've defined is that the distance between any point and itself is equal to 0. So this is obviously very helpful in satisfying our first condition, because we've just simply defined it as such. And also that the distance between any two distinct points at all, is exactly equal to 1. So the distance between say for example this point and this point is 1. The distance between this point and this point is 1. The distance between this point and this point is 1. All the distances between every single point is equal to 1. It doesn't matter about the length of the line. Remember, this is just an abstraction. So essentially all of this is just visual nonsense, but it's interesting visual nonsense. So how do we prove that this is a metric? Well, obviously the first condition is satisfied quite trivially because we've defined it. The second condition of symmetry is obviously satisfied because any distinct points, the distance between them is just equal to 1. Doesn't matter if we put y first or x first, it's still equal to 1. So what we have to prove is the triangle inequality, and this is pretty simple as well. Let's just take a look at it again. And so obviously if x and z are not distinct points, then this distance will be less than this expression on the right hand side, because this will be 0. So we have to consider what happens when x and z are distinct. Well, if x and z are distinct, let's just draw it. So d of x of z, let's do the numbers underneath. So this is 1, and so what's the least possible value that the d of xy plus d of yz could take for any possible value of y? Well, if y is distinct from both x and z, then obviously this expression here would be 2, and so it would be greater. So what's the least value? Well, it would be if y equals one of these points. But obviously it can't equal both of these points, because these are distinct points. So it can equal at most 1 point. So let's, without loss of generality, just assume that it equals x, and then this is 0 and this is 1, and so this is the absolute least that this expression can take. So this is satisfied. So you just need to understand that this metric can be applied to any set, any space, doesn't matter. Even continuous spaces like the two-dimensional plane, just define the distance between any 2 points equal to 1. Let's do another one. So this one is called the max metric, and the reason why will become clear in a second. Max metric, and this is another metric on n-dimensional real space. Remember, we can have as many different kinds of metrics in addition to the normal Euclidean metric, which we're all familiar with. So this takes 2 points in n-dimensional real space and maps them to the maximum for 1 less than or equal to I less than or equal to n, where n is the number of dimensions of the distance between each component. So this is the set of distances between each component, and we're just taking the maximum possible value of the distances between the components as our total distance. So if I just draw this in I won't try to draw it in 3D space, but in 2D space, if we just take this, basically what we're saying is, let's take a point x and a point y here, say, and what we're saying is, let's define the distance between these 2 points as the maximum value of the component differences. So this is, the component and the distance between them in one direction, and this is the distance between them in the other direction. Let's take the biggest one, this one, to be our distance. But we're doing this for, remember, n-dimensional space, not just 2-dimensional space. So just imagine a space with lots of dimensions, and just take the biggest difference in any one direction to be our distance. So the first 2 conditions of a metric should be really obvious that this satisfies these, right? It should be screaming at you like, I'm symmetric, or not. But let's take the triangle inequality. Let's take the bigger term in the triangle inequality and evaluate it like we did with the Euclidean metric. So this is d of xy plus d of yz. Now what are each of these? Well, these are the maximum possible values of the differences between each of the components. So this expression is going to be greater than or equal to xi minus yi plus yi minus zi for all I. But notice what this is. This is just the Euclidean metric in one-dimensional space. This is one point minus another point on just the straight line. So this is the distance between xi and yi in the Euclidean metric, and this is the distance between yi and zi in the Euclidean metric. But we know that the Euclidean metric is a metric, so we know that this, by the triangle inequality, as it's satisfied by the Euclidean metric, then we know that it's greater than the distance between xi and zi. For all I. But if it's bigger than xi minus zi for all I, then obviously it's bigger than the biggest xi minus zi. So, but the biggest xi minus zi is the metric between x and z. So this is bigger than the distance between x and z. And so we proved that the max metric is in fact a metric. Okay, so let's do another one. It's the last example. This is called the taxi cab metric. This one is it's kind of funny. Taxi cab metric, and this is defined on z squared. Well, you can define this on any geometric space, I guess. So z squared. I just find it makes more sense in z squared, and we haven't seen one in non-real dimensional space. It's multi-dimensional, so we'll do it in this. And this takes 2 points x and y and maps them to the absolute value of x1 minus y1 plus absolute value of x2 minus y2. And what does this mean? Well, let's just draw out z squared space. This will be just a grid of points, equidistant points spaced out. And if you imagine this like a city, or like Manhattan, where it's all blocks and streets, then if you have say this is our point y up here in the top, and this is our point x down here, then this metric is basically just saying, well, it's the distance in one direction plus the distance in that direction. Basically means the number of streets that you need to drive through in order to get to your destination. So it doesn't matter which way you go, it's still going to produce the same distance, because it's we're trying to model a number of streets that we need to go. So For example, if I go this direction, it's going to be the same as if I go in some other direction, like this way. Then I just have traveled the exact same number of streets. And so, again, we'll prove the triangle inequality for this. Just notice that this is just, I mean, literally defined the sum of two different Euclidean metrics. Granted, they're defined on integer space instead of real space, but it doesn't make a difference. We'll just prove it. So the distance between x and y plus the distance between y and z, well, this is equal to x1 minus y1 plus x2 minus y2 plus y1 minus z1 plus y2 minus z2. And so all we have to notice here is that these two are greater than x1 minus z1, just because they're the Euclidean metric, and these two are bigger than x2 minus z2. Well, what is this sum, this orange sum here? Well, this is just simply equal to the taxicab metric between x and z. And so that concludes our metric examples. And next video we'll be talking about open balls in metric spaces.